to responsibly explore other planets and moons in our solar system. In order to do that, we need to make sure that we send a clean spacecraft there. We would hate to get to another planet or moon and think we discovered life, but it was actually something that we brought with us. So we collect our samples on InSight, any part of InSight that's going to land on the surface of Mars. We bring it back to our lab and we process it using a NASA procedure. If we run into a situation where we take a sample and it comes back as having a higher number of bacteria than what we want, then we make sure that the engineers go back and clean those surfaces with the whole idea that we don't want to cloud our ability to potentially find life on another planet or moon.
Lockheed Martin Space of Denver, Colorado, built InSight with an extremely efficient design, streamlining what needs to be done at the launch site. They shipped the spacecraft to Vandenberg with no assembly required. Simply check it out, fuel it, test it, encapsulate it, and it's ready for launch.
The processing for our spacecraft has been very smooth. A lot of the processing had to do with fueling the spacecraft, removing some remove before flight items. Everything else was pretty much already installed on the spacecraft in Denver, Colorado before it was shipped here. And that's called a ship and shoot, which means there's not too much to do except for to fuel the vehicle and do some last minute power on checkouts of the onboard computers and subsystems.
These preparations are crucial. Everything must be working perfectly before InSight leaves Earth. This effort is designed to ensure a safe arrival and landing following the 6-month trip from Earth to Mars. In the meantime, United Launch Alliance, or ULA, is busy at their launch pad, Slick 3, assembling the world's most successful rocket, the Atlas V.
Well, I mean, we're building a rocket. What's not exciting about that? And really excited to be able to launch the first planetary mission from the West Coast.
First, ULA stacks their Atlas V booster onto the launch platform. Atlas V is powered by the mighty RD-180 rocket engine. The RD-180 is a powerhouse, burning highly refined kerosene known as RP-1 and liquid oxygen for thrust. For this mission, the RD-180 has more than enough power to get InSight off of Earth and heading towards Mars. When the booster's fuel is spent, the Centaur second stage kicks in and finishes the job. Centaur won't actually hit Mars. It will fly just past it. Final course corrections will be done by InSight itself to enter the Martian atmosphere and land on the surface. Once fueling and testing is complete, the team from United Launch Alliance will encapsulate InSight inside its payload fairing, the shell that keeps InSight clean and safe during its dangerous ascent through Earth's atmosphere.
We're at the phase of the mission where we're encapsulating with the launch vehicle, and the ULA team with their fairings now come in and they take the two halves of the fairings and they make a clamshell around the spacecraft to help protect it for the environments that we see during launch. And we do that because as we leave the Earth's atmosphere, the air and the molecules in the atmosphere would tear up our spacecraft otherwise, and the fairing is there to protect us.
With InSight encapsulated in its fairing, it's time to move the payload out to Slick 3. But this California coastline comes with its own set of challenges. The surrounding marine layer can swallow up a launch pad, reducing visibility to under a couple hundred feet.
So right now, it's on the transport vehicle and it's ready to roll. And we'll be rolling out around 2 a.m. At that point, we'll have a convoy that drives very slowly from the payload processing facility out to the Slick 3 Atlas V facility. And once it arrives, we'll hoist the encapsulated spacecraft up to the top of the mobile service tower and place it on the launch vehicle.
This morning when it was sitting on the truck and they put the crane on it, they started to lift it up. That's the last time this spacecraft's ever going to feel the ground of Earth. I'm just kind of jumping out of my skin. This is so exciting. We're getting so close to launch, and it's been a long, long road for me. This has been a challenging program. I mean, we've had a lot of technical issues to overcome. We actually had to stand down back in 2015, but since then we've gotten it all together, and things have been going so smoothly the last year. we really feel really confident about this launch now. We got it on top of the rocket. We're going to blast it off in just a few days, and when it gets to Mars and lands, finally it will have solid ground under its feet again and get to work on probing the depths of Mars.
But InSight won't be traveling alone. Hitching a ride to the red planet are a pair of CubeSats, twin satellites called Marco A and Marco B.
So Marco is a dual payload riding as a secondary mission on its way to Mars.
So Marco is a pair of CubeSats, and CubeSats are really small spacecraft. They're essentially the size of a large cereal box, so about this big.
It's going to be relaying telemetry from the entry, descent, and landing of InSight back to Earth in near real time. After InSight is deployed on orbit and is heading to Mars, Centaur, which is behind me, ejects Marco A into orbit, and it'll slowly rotate itself so that Marco B ejects 180 degrees on the other side of the vehicle.
But Marco is a technology demonstration mission. It's actually one of the smallest spacecraft we've ever launched to interplanetary space. It's the first interplanetary CubeSat. So in of itself, it has all of these technology that we've never tested in deep space before. So if Marco works this time, one of the cool things that we could do is actually replicate that system and fly it with other missions in the future. And whether you're going to Mars or Venus or maybe even further away to an asteroid, you could think of it as bring your own telecom relay.
So everything went well today with the lift of the spacecraft and mate onto the rocket. It started off very foggy and windy, and right now it's a beautiful day, just typical California weather. And now we're ready to go to Mars.
But just as twilight falls across the base, the fog returns, cloaking the coast with a bone-chilling mist that will last until daybreak.
As we get closer to T0 liftoff time, a number of activities have to happen. There's a mobile service tower around the Atlas V rocket, and the InSight spacecraft is on top of the rocket, enclosed in the payload fairing. So we're going to back that mobile service tower away from the rocket to leave it exposed just beside the umbilical tower.
Stand engineer, proceed with MST roll to park position. Roger. MST bores shall be closed in park position. Roger.
The final launch pad preparation is underway. Once the mobile service tower is rolled back, InSight and Atlas V are just hours away from T0. Basking in the searchlights of the West Coast facility, they are presented with the glamour of a Hollywood premiere, fitting treatment for such an historical mission.
So there's a lot of excitement within the NASA launch team about the InSight mission. First time we're going to launch from the California coast, going to Mars. And what is really exciting to the team is this is the culmination of a lot of work. The teams have been working on this mission for over 5 years, and today is the day that they will see all of their hard work rewarded.
Status check to proceed with terminal count. Atlas systems. Propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems. Propulsion. Go. Pneumatics. Go. LH2. Go. Facility. Go. Range coordinator.
Clear to proceed.
Launch director.
LC, you have permission to launch.
Go Atlas. Go Centaur.
Go InSight. Proceeding with the count.
We're at T-minus 8, 7, 6, 5, 4, 3, 2, 0. And liftoff of the Atlas V, launching the first interplanetary mission from the West Coast, and NASA's InSight, the first outer space robotic explorer to study the interior of Mars.
Seconds after liftoff, the rocket punches through the marine layer, lighting the night sky for miles, visible all the way down to Los Angeles. An infrared camera showing the long tail of the exhaust plume captures some of the ascent, as well as an onboard ascent camera.
And we're nearing booster engine cutoff, or BECO.
Back to 4.6 Gs in preparation for BECO. Boost phase cooldown has completed. And we have BECO. Shutdown looks good. Stage separation. We have box and fuel pre-start. G&2 purge firing. The RCS is underway. We have ignition and full thrust. And we have indication of payload fairing jettison. Looks like a good step.
And the payload fairing that was encapsulating the InSight spacecraft has been jettisoned. The RL-10C engine, the second stage of the Centaur, continues to burn.
An hour and 28 minutes into the mission, the InSight spacecraft and the Marco twins are deployed from the Centaur upper stage, beginning the long voyage to Mars, where InSight will go to work shedding light on secrets hidden in the depths of the Red Planet.
Advanced Air Mobility, or AAM, is this vision of a new mode of transportation that will enable the safe and efficient movement of people and cargo by air to and from locations that are currently only accessed by road. One area the NASA team is researching is passenger ride quality. NASA's Advanced Air Mobility mission is researching what ride quality could be like for passengers traveling in eVTOL aircraft to make sure it'll be a smooth and safe ride. The idea is to conduct research on human subjects by studying their physiological response to the types of low-frequency motion, vibration, and noise stimuli that we expect AAM passengers will experience. We believe AAM aircraft will need to be designed smartly. They will need to be conducive to low cabin noise and low vibration from the rotors. They will need to be more resistant to being upset by turbulence. And they will need to be operated or flown in a predictable, repeatable, non-aggressive manner that will not result in large accelerations or sudden accelerations or rotations of the aircraft. It's really exciting to see the amount of innovation that is going on in the aerospace industry. It is truly a fascinating experience to see all these new designs come forth.
We're never going to stop exploring the unknown in air and space. We're not going to stop innovating for the benefit of humanity and inspiring the world through discovery. 22 will go down in the history books as one of the most accomplished years all of NASA's history and missions. The golden age of space exploration. So much to look forward to in 23. Climate missions that will tell us about how our Earth is changing. Game-changing aeronautics developments with the 59 and the X-57, and the selection of the first astronauts to go to the moon in more than 50 years. And there's a lot more coming. There was a philosopher, a historian, someone who had a great grasp of the future named Carl Sagan, a scientist. And he said, exploration is in our nature. We began as wanderers and we are wanderers still. We have lingered long enough on the shores of the cosmic ocean. We are ready at last to set sail for the stars. We have set sail for the stars. Now we're going to reach out to the unreachable stars.
Hi everyone, welcome to NASA's Goddard Space Flight Center. My name is Elizabeth and I'm the social media lead here for the Hubble Space Telescope. And we're live now with some really big news from Hubble. And here to tell us more about it, we have Dr. Jane Rigby with us, and she's a co-author of the result that we're going to be talking about, and also the operations project scientist for the recently launched James Webb Space Telescope. And we also have with us Dr. Patty Boyd, who previously worked as the Deputy Operations Project Scientist for Hubble and now works as the Chief of NASA's Exoplanets and Stellar Astrophysics Laboratory. Thank you both so much for joining me today. I'm really excited to hear about this Hubble news. And for anyone watching live, if you have questions during the stream, please feel free to comment them, and we're going to do our best to get to some at the end of the show. But for now, I think we should just jump right in. So, Patty, it sounds like Hubble just broke a pretty impressive record. Could you tell us what Hubble discovered?
Sure, I would love to. And it's really exciting to talk about this record-setting star. So, like so many other discoveries from Hubble, it starts with an image, a very beautiful image. And one of the first things that you can see in that image are galaxies. And those galaxies are actually gravitationally bound in a cluster. Those are fascinating objects in the universe. They have a huge amount of mass. And what's very special about this particular image, in addition to that beautiful cluster of galaxies, is that it actually contains an image of a single star whose light left that object when the universe itself was less than 1 billion years old. So this is a rare event, and we're really excited to learn more about this object.
Yeah, that sounds super exciting. And just as a refresher for everyone, Hubble has been orbiting Earth for almost 32 years and is still generating incredible science like we just heard about. So Patty, could you also tell us just what can astronomers learn about our universe by examining this star?
So when we look at the stars in our own neighborhood, like when you look up at the night sky, those stars are in our Milky Way galaxy. They're in the same galaxy that we're in. We're a star, one of 100 billion or more in the Milky Way. And those stars evolved a lot like we did in this same Milky Way galaxy. And they're about, thousands of light years away from us when we look at them. So the light that from those stars is coming to us thousands of years later. When we're looking at this star called Earendel, we're looking at the universe itself when it was like in its first billion years. We're at 3.8 billion years now. The universe has changed a lot in that time. So Earendel is this rare window when we can actually look back and see how stars were working in those very early days of the universe.
Wow, that's very interesting. Thank you. And another cool part about this observation is that it was only possible because of an astrophysical phenomenon known as gravitational lensing. So Jane, can you kind of break down for us like what gravitational lensing is?
Sure. So we can see the star, even though we're looking back so far in time, because of two things. One, the speed of light's not that fast, right? So we're able, as Patty was saying, we look back in space to look back in time. And the other is this phenomenon of gravitational lensing, which is just the fact predicted by Einstein that mass bends space. And so light is traveling through a curved space-time, and so it acts like mass is bending light, gravity is bending light. Well, if you think about it, what happens when you're bending light? Well, eyeglasses are bending light, right? They're getting the light to change where it shows up in your eyeball so you can see better. So it turns out that this phenomenon of gravitational lensing, when you get big concentrations of mass, either a galaxy or better yet, a cluster of galaxies together, they can act like a cosmic telescope and bend the light, focus it toward, accidentally, toward us. And so this is a really rare phenomenon. About maybe 1 in 1,000 to 1 in 10,000 galaxies are gravitationally lensed. But when this happens, we can take advantage of these cosmic telescopes and then observe them with our human-built telescopes to see way farther than we normally can. And those background galaxies, they're way behind the cluster. They don't have anything to do with the cluster. We see them not only much brighter than they really are, but stretched and magnified, kind of like they're in a funhouse mirror. And that lets us study them in greater detail than we normally can with our current telescopes.
Okay, gotcha. That's really cool. And so another thing I'm wondering, like, how did astronomers, when they were making this observation, know that Earendel was an individual star rather than a bigger cosmic object?
Sure. So this is a cool case where this is a discovery that was half on purpose, half, oh wow, that's cool, which is how a lot of science works. So the cluster and the Lens galaxy were found in 2016 by Dan Coe and collaborators. And so they found the arc and said, okay, that's a very high redshift arc, redshift 6, a Lens galaxy at redshift 6, about 1 billion years after the Big Bang is how we see it. And so, and then Brian Welch, a graduate student at Johns Hopkins, was given the task of modeling this thing and doing the lens model of where's all the mass in the cluster and getting that to reproduce the distorted shapes that we see of the Lens galaxies. And as he was doing this, there's this dot in the middle of the Lens galaxy. And try as he could, that dot had to be really small in all the models, like super small, like the size of our solar system. And the magnification had to be really high, like thousands. And so the most obvious explanation is that we're seeing either one star or maybe a couple stars, but it's not like a big star cluster, but we're seeing down to the scales of individual star or multiple stars all the way out 1 billion years after the Big Bang.
Okay, wow. And speaking of, this star being within the first 1 billion years of the Big Bang, Patty, how did astronomers know that about this star? How did they know it was in there?
That's a great question. And so, like many of the images that Hubble takes of these fields, these treasury fields, we're observing them to collect as much data as not only the team wants to get the science that they want to get out, but that the entire community can really mine that rich archive and get a lot of science out. So one of the ways you can get the most science out of an image like this is to observe it in multiple filters. And the filters are basically different colors of light. So they specify a certain range of colors. And so this is a multicolor image using 2 instruments on the telescope. And what that allows us to do is, for the galaxies, each galaxy is going to have a certain brightness in those filters. And we can look at how that brightness changes as a function of our filter. And what we see with these objects that are very far, they're redshifted. We call it redshifted. As they move further from us, the whole universe is actually expanding. The light gets shifted into the red. And what that will do to a galaxy's spectrum that's far redshifted is it'll actually kind of block it out in the optical. You won't see the light there. It'll just start to peak out the redder and redder that filter gets. So if you notice in the image that smear that we're looking at, the sunrise arc it's called, it's very red compared to the rest of the image. And that's why, is the light's just starting to pick up as we go redder. And you can use that to estimate its redshift. And that is exactly how the objects in that arc are estimated. They're all at about the same redshift of 6.2. And you use that number and the photometric information that you have to estimate everything else. Its distance and then its size scale is related to that. So there's just a tremendous amount of scientific information in these multicolor images, in addition to just the beauty of looking at the galaxies that are in them.
Oh yeah, for sure. And Patty, also, why is it important to be studying this star that is within the first 1 billion years of the Big Bang?
So when we look around at our local universe or the stars in our own galaxy, we get a picture of how the universe has evolved. And one of the coolest stories about that is where matter came from, where the heavy elements came from, where the carbon, calcium, oxygen that makes up everything, our bodies, our bones, our telescopes, where did those elements come from? And the answer is that they're fused in the centers, in the cores of stars. And massive stars in particular are very efficient at this. They fuse lower elements like hydrogen and helium into heavier elements, and then they explode in supernova explosions, and they spew that material out into their local environment so the next generation of stars can pull that in as they're forming. Those are the kind of things that form rocky planets like the Earth, where we've got an iron core and all those elements in our atmospheres. Those were fused in earlier generations of stars. So Arundel is this single star, the farthest yet that we've been able to observe, and it will allow us to see how that process started to be put together in the very earliest days. When did those very early heavy elements start to be infused into the material? And it's just a window that's opening up onto, the next big thing, because that light is pushed so far into the red that we need a telescope that can go even further into the red than Hubble can to really uncover the cool things.
Yeah, and speaking of, I think another fantastic part about all of this is that there's already approved observations to look at Arundel with the recently launched James Webb Space Telescope, which is a super powerful infrared space telescope that just launched in December. We're so excited for it to begin science operations this summer. And Jane, could you kind of tell us how Webb might bring this Hubble discovery even farther?
Sure. So I learned about this lens star when the discoverers came to me, said, so do you want to be, we're trying to figure out how to plan some Webb observations. Are you in? I'm like, oh, I'm totally in. That's cool. So what we worked out was a set of observations with NIRCam, which is the near-infrared imager, to get colors in all of those filters that are too red for Hubble to do well, right, or to do at all, right? And so Webb will pick up where Hubble left off, getting redder filters. So we'll have very crisp, gorgeous images. We've already proven with Webb that we can take gorgeous images. It's as a very, very sharp telescope. And now we're getting the science instruments ready to go. The second science instrument that we will target for this galaxy and star is NIRSPEC, the near-infrared spectrograph. And so we'll be taking spectra of not only the lensed galaxy, the sunrise arc, but also the star Arundel. And so the NIRSPEC has a lot of cool bells and whistles. One of them is it has this microshutter array that has 250,000 doors that can open and close magnetically. And so we'll open up doors, we'll close most of them so we don't get the brightness of the sky in the way. And then we'll just open some doors for the lens galaxy and for Arundel the star. And we'll be getting spectra, right, with a little prism to tell us about what's inside that galaxy. What is the temperature of that star? How bright is it really? How, as Patty was talking about, how much of the heavier elements that were made in stars are in this galaxy versus just the boring hydrogen and helium that's made in the Big Bang?
Okay, gotcha. And so more broadly speaking, why is it important that both Hubble and Webb are going to be operating at the same time?
Sure, so Hubble and Webb are really complementary. They're not really in competition. When we built Webb, we knew full well there was a Hubble up there doing great stuff, and we didn't try to replicate that functionality. So it's really like players in a band, like your drummer and your keyboardist are doing different things. And so you select them for different skills. So Webb is really designed to do the things that Hubble can't. It has much greater spectroscopic capabilities than Hubble, so we can really see what the universe is made of, which is great because that's part of what my research is. I love spectroscopy. What's stuff made of? And then the other part is that we're operating in the infrared with Webb. So we're looking, the bluest light that Webb can see is like a dusky red, like red wine. And then it just gets redder from there, right? So whereas Hubble can see into the near infrared, and then it can see pretty hard into the ultraviolet, like bluer than cats or bees can see.
Okay, yeah. It's going to be really great. I'm very excited for them both to be working together up there. And back to Hubble, Patty, could you just sort of tell us how Hubble's doing these days? How long we can expect it to last?
Sure, absolutely. So Hubble is actually doing great. And it was launched in 1990, so it's coming up on its 32nd birthday in space. That is a long time for an observatory to be in space. It's in a low Earth orbit, and its orbit was chosen so that it could be rendezvoused with the space shuttle. And astronauts could actually grab it and bring it back into the bay there and service it. What servicing meant was that it could refurbish the instruments, refurbish the computer, the power systems, and this was done 5 times during the lifetime of Hubble. During the last servicing mission, the astronauts worked very hard to leave the telescope at the peak of its capabilities. And ever since then, there's been a team of engineers and scientists working together on the ground to extend the lifetime as much as possible. So we're expecting Hubble to continue into the next decade so that we can squeeze as much great science out of Hubble as possible.
That's fantastic. Thank you, guys. All right, so bear with me for a second. We've been getting some questions from social media, so let's see if there's anything we can talk about here. Okay, so We did talk about this a little bit earlier, but maybe, Patty, if you want to go into this a little bit more. Someone on YouTube is just curious, more knowing about how we can tell this is a star rather than, a galaxy, basically. Or Jane, if you want to take that one on,
Sure.
either way.
I can take that one.
Okay.
So the main constraint that it has to be really small. So the main constraint is that it's really small and really bright. And so the size constraint comes mostly from the fact that in the images, it looks like a dot. It's round. It isn't stretched. And if it had any significant size, like bigger than the size of our solar system, then given the really high magnification, we would see it stretched. But we don't. We see it as a dot. And so that places a really strict limit on the size. In the paper, we give it in terms of, but they're all about the size of the solar system. So it's got to be smaller than like out to Pluto, right? So that's one constraint. It's got to be something that fits in a small box. Okay, and given that really high magnification, something like thousands, and it's whether it's 1,000 or 10,000, we showed a bunch of different models to show that it's somewhere in that range, okay? So you have something that's given its brightness and magnified by factors of 1,000, well, that's like 1,000,000 times the mass of the sun, 1,000,000 times the luminosity, the brightness of the sun, okay? So, all right, what is out there that is bright as 1,000,000 suns and fits in our solar system? Well, that's really very massive stars, or binaries, could be binary, or it could be a accreting black hole. But we also know it hasn't changed in brightness. So we have observations. Hubble has observed this star multiple times, in part to look for supernova, to look for lensed exploding stars. And in those multiple epochs, we don't see any sign that it's changed brightness. So one of the characteristic features of accreting black holes is that they go up and down in brightness and they change. And so we think the most likely explanation in the paper is that this really is a massive star.
Yeah, okay, makes sense. Thank you. Awesome. Well, thank you all so much for sending in these questions on social media. I think we are unfortunately running out of time for today, though, so we're going to have to wrap things up. But thank you all for tuning in to learn more about Hubble's discovery of the farthest individual star ever seen. This is a really cool story, so if you want to find out more, be sure to check out nasa.gov/Hubble. And as always, you can keep up with Hubble on social media at NASA Hubble on Facebook, Twitter, and Instagram. Thank you all so much for joining us today, and have a great weekend. Bye, everyone.
Advanced Air Mobility, or AAM, is a new transportation system that allows us to get between cities, allows us to move passengers and cargo on an on-demand fashion. It's new and exciting. It allows us to have these new vehicle configurations that were never dreamed of before. So AAM is the way of the future for aeronautics. One area that NASA's AAM team is focusing on in their research is the area of vertiports. A vertiport is where these new class of AAM vehicles can take off and land vertically. It needs less real estate, less area than an airport, and allows us to access different parts of the city that were previously inaccessible by helicopters because of loud noise. NASA's Advanced Air Mobility mission is going to help integrate these vertiports into some of the existing infrastructure and allow to add places for electric vertical takeoff and landing vehicles, or eVTOLs, to take off and land in cities and suburbs. These AAM vehicles are going to be electric in their nature. They're going to require power sources going to those helipads. And then the density of operations is going to be such that there's going to be a lot of aircraft taking off and landing, which requires potentially other systems such as automation. Our research is focused on trying to enable a new system where automation helps at large scale and allows for both safety, security, and efficiency, and to make sure that you as a passenger get from one point to another on time and safely.
it's extremely exciting. In my lectures, there are always young people in the audience,